Good morning, everyone. Today we are excited to present our project, a real-time audio spectrum and noise detection system built entirely in Python. Say the word hello. In the air, that's just a smooth wiggle of pressure and analog system. What happens when I plug a mic into a device and capture it? The wave becomes a graph of amplitude over time. Peaks and valleys, your voice literally drawn. This is signals and systems in action. A signal is any measurable variation, sound, light, voltage. A system is whatever transforms it. The mic turns air pressure into voltage. An A to D converter samples it. Tiny snapshots taken thousands of times per second. More samples, more detail. Too few and the signal gets jagged or even misread. Now the fun part. Turn time into frequency using a fast Fourier transform. The device decomposes the wiggly wave into ingredients, pure tones. Here's the frequency graph. Low bars for bass, high bars for treble. Their height shows strength. Your voice isn't one. Note it's a chord of fundamentals and the harmonics that shift as you speak. The peaks clustered higher. Peaks slide lower. Those moving peaks formants are your voice fingerprints. If I plot frequency against time with color for intensity, I get a spectrogram, a heat map of speech. Consonants look like bursts. Vowels paint steady bands. Why process signals? To clean noise, compress data, recognizing patterns. A noise filter suppresses hiss by certain frequency bands. A pitch shifter moves everything up the scale. Auto-tuned imagining. Anywhere waves become information. So speak, sample, transform, visualize. From breath to bars. From time to frequency. That's the map of sound. In this video, we will break down the core tools, sampling, convolution, filtering, and the Fourier family so you can read and reshape any signal. Ready to see your world as waves? Let's start.
Now, let's move on to the code explanation, where we will see how our real-time audio spectrum and noise level detector actually work. We are importing three Python libraries: Sound Device to capture live audio, NumPy for quick math calculation, and Matplotlib to visualize our sound wave. Then we set our sampling rate and duration, basically how fast and how often we record sound. Finally, a noise threshold is set, that's the limit beyond which our system wants if the environment gets too loud. This function captures a short audio segment from the microphone and performs three key operations. First, it measures the loudness of the sound, then applies a fast Fourier transform to analyze its frequencies, and finally return both the sound intensity and its spectrum. This helps us break down what we are actually hearing in terms of both volume and tone. Let's make it visual now. Here we are creating two live graphs, one for the time domain and one for the frequency domain. The top one shows sound changes over time like a regular waveform. The bottom one breaks that same sound into different frequency components, basically showing which tones or pitches are strongest. It's like seeing your voice in motion. This simple logic classifies sound based on those extracted features. If the energy is too low, it's silence. If the signal changes too quickly, it's likely a background noise. When a stable pitch is detected, it classifies between male and female voice based on the frequency range. It's a smart and lightweight way to detect what kind of sound is being captured, all in. And finally, if we connect everything together, the program continuously listens to live audio, processes it, extracts key features, and instantly classifies what it hears, whether it's silence, noise, or human voice. In simple terms, our system listens, analyzes, and identifies sound pattern in real time, combining both digital signal processing and intelligent classification.
In this system, we analyze live audio from a microphone and classify it based on its frequency characteristics. The output is not constant because human voice, noise, and music all change continuously in time. The fluctuations you see on the screen are expected. They simply indicate that the system is reacting in real time to whatever sound is present. Sometimes the system may classify steady human voice as music because long vowel sounds look similar to a musical tone in the frequency spectrum. This is not a fault. It is a natural behavior of spectrum-based classifiers which rely on frequency content rather than language or meaning of speech. Overall, the live fluctuation and class switching demonstrate that our analyzer is detecting and updating sound categories dynamically based on actual audio input. Now we will discuss application of our project in home automation. An audio spectrum analyzer does not just capture sound, it understands the frequency pattern of the sound. This allows a smart home system to react only to specific sounds like claps, whistles, or voice tones instead of reacting to random noise. For example, a clap can turn on lights, a whistle can open curtains, a sharp high frequency sound like glass breaking can trigger a security alarm, and a low frequency pattern like a knock can unlock a door. Because the system analyzes the spectrum, it is more accurate and intelligent than a simple sound sensor. It enables touchless, real time, and reliable home control using just sound. Thank you.